There is a silence in the cosmos that we can never truly know. It is a quietude born not of peace, but of vacuum, an emptiness so profound it stretches between worlds, across the gulf of galaxies. For billions of years, from our small blue oasis, we have always looked up into it. We have charted the serene, predictable waltz of the planets and connected the distant points of light into comforting myths. We imagined the heavens as a clockwork masterpiece, a reflection of order, a divine and tranquil ceiling. We were profoundly, beautifully, and terrifyingly mistaken. The serene night is an illusion. The quiet is a lie, a veil drawn across a theatre of such violence and bewildering peculiarity that it beggars the human imagination. Our telescopes, our probes, our calculations, they are not just tools of measurement. They are windows into a cosmic asylum, a universe far stranger than we ever dared to dream. The things we have found out there in the great darkness do not just challenge our science, they challenge our sanity, our very definition of what is real and what is possible. This is the story of those discoveries, the story of the anomalies, the monsters, and the ghosts that haunt the fabric of space-time. Our journey into the bizarre begins with an idea of endings. For eons, we saw the stars as eternal fires, immortal beacons, but we now know that they live and, more importantly, they die. And some die in a manner so spectacular, so catastrophically violent, that their death rattles echo across the universe. When a star many times more massive than our sun runs out of fuel, its own colossal gravity, a force held at bay for millions of years, wins the final, decisive battle. The core of the star collapses inward upon itself. It falls at a quarter of the speed of light, an unstoppable implosion that triggers a final, defiant explosion, a supernova. For a few weeks, this single dying star can outshine its entire galaxy, a final, glorious scream into the void. But what of the corpse it leaves behind? What remains at the heart of the fire? For the most massive stars, the answer is a gateway to infinity. But for a slightly smaller class, the remnant is something else. Something that stretches the laws of physics to their breaking point. Imagine taking a mountain, not a small one, but Mount Everest. Visualize its sheer scale, its 8,800 meters of rock and ice. Now, imagine taking not just that mountain, but the entire Himalayan range and crushing it, compressing it with an impossible force, until all of that mass, all of that substance, fits into a space no larger than a common sugar cube. The object you are holding in your mind is a pale imitation of the reality of a neutron star. These are the densest objects in the known universe that are not black holes. They are the collapsed cores of giant stars, stellar zombies, packing the mass of 1.5 of our suns into a perfect sphere only 20 kilometers across, a city-sized star. If you could somehow acquire a single teaspoon of its material, that spoonful would weigh over 1 billion tons on Earth. It would plunge through the planet's crust and mantle as if they were nothing more than mist. Its surface gravity is 200 billion times stronger than Earth's. Its magnetic fields are 1 trillion times more powerful. It is an object so extreme, its very existence sounds like a fiction. First theorized in the 1930s by Walter Baade and Fritz Zwicky, they were considered little more than a mathematical curiosity for decades. How could matter possibly behave this way? The answer lies in the fundamental nature of reality. The immense pressure of the gravitational collapse is so great that it overcomes the forces that keep atoms separate. Electrons are smashed into protons, merging to form a sea of pure neutrons, packed together as tightly as the universe will allow. It is a single, gigantic atomic nucleus the size of Manhattan. This is no longer matter as we know it. It is neutronium. In 1967, a young graduate student named Jocelyn Bell Burnell, working at Cambridge University, was monitoring data from a new radio telescope. She noticed a strange, repeating signal, a pulse so regular, so precise, it beat like a cosmic metronome every 1.33 seconds. For a moment, the team entertained the most tantalizing of possibilities. Was this a beacon? A message from little green men? They labeled the signal LGM-1. But soon they found other, similar signals from other parts of the sky. They had not discovered aliens. They had discovered something perhaps even stranger. They had found the neutron stars. These objects spin at incredible speeds, hundreds of times per second, and as they whirl, their intense magnetic fields channel beams of radiation out into space from their poles. If one of these beams happens to sweep across our line of sight, we see a pulse of radio waves. A celestial lighthouse, spinning in the dark, the ghost of a long-dead sun, still screaming its existence across the void. But what happens when the dying star is even more massive? What happens when the force of gravity is so absolute, so completely unopposed, that not even the dense packing of neutrons can stop it? The answer is the most enigmatic and terrifying concept in all of cosmology. The collapse does not stop. The core continues to shrink, past the size of a city, past the size of a marble, past any dimension we can comprehend, into an infinitely small, infinitely dense point of singularity. Around this point, gravity becomes so powerful that it warps the very fabric of reality. It creates a one-way door in the universe, a region of space-time from which nothing, not even light itself, can escape. It creates a black hole. The idea is not new. As far back as 1783, the English natural philosopher John Michell speculated about dark stars, objects so massive that their escape velocity would exceed the speed of light. Later, Einstein's theory of general relativity provided the mathematical framework. His equations showed that mass doesn't just pull on things, it bends the geometry of space and time around it. Imagine space-time is a vast, flat, rubber sheet stretched taut. A planet like Earth places a small divot in this sheet. Other objects rolling nearby follow the curve, creating what we perceive as an orbit. Now, imagine placing an object of immense density on that sheet. It doesn't just create a divot, it punctures a hole right through it, an infinitely deep well from which there is no return. This is a black hole. The edge of this well is called the event horizon. It is not a physical surface, but a threshold, a point of no return. Crossing it is an irreversible act. Once you pass the event horizon, all possible paths in spacetime lead in only one direction, toward the singularity at the center. The future becomes a place, not a time. For decades, these two were just theoretical monsters, lurking in the complex equations of relativity. But the evidence began to mount. We saw stars orbiting, nothing, vast, empty points in space, with stellar partners whipping around them at incredible speeds, tethered by an unseen, immense gravitational force. We saw matter from companion stars being siphoned off, forming a swirling, superheated disk of gas around the black hole. As this material spirals to its doom, it is heated to millions of degrees, blasting out X-rays that our telescopes can detect, the final, agonizing scream of matter before it is silenced forever. And then, in 2019, humanity achieved the impossible. The Event Horizon Telescope, a global network of observatories acting as a single Earth-sized lens, captured the first ever direct image of a black hole silhouette. It was a monster named M87*, 6.5 billion times the mass of our Sun, residing in a galaxy 55 million light-years away. The image was not of the hole itself, for that is by definition invisible. It was a picture of its shadow, a perfect circle of blackness, backlit by the ghostly glowing ring of superheated plasma, trapped in its gravitational embrace. We had stared into the abyss, and for the first time, the abyss stared back. The black hole was no longer a theory. It was real, a fundamental breakdown of our known physics, a wound in the universe, existing in plain sight. The universe, it turns out, is not only filled with visible monsters. The most profound strangeness lies in what we cannot see at all. For most of the 20th century, we built our models of the cosmos based on the things we could detect: stars, gas, dust, galaxies. We added up all the light, calculated the mass, and assumed that was it. We were off by 95%. The story of this revelation begins in the 1930s with the brilliant, if famously cantankerous, Swiss astronomer Fritz Zwicky. While studying the Coma cluster of galaxies, he noticed something deeply wrong. The galaxies within the cluster were moving far too quickly. Based on the visible mass of all their stars, the cluster shouldn't have enough gravity to hold itself together. The galaxies should have flown apart, dissipating into the void ages ago. Zwicky proposed that there must be some form of unseen matter, which he called dunkle materie, or dark matter, providing the extra gravitational glue. His idea was largely ignored for 40 years. Then, in the 1970s, an astronomer named Vera Rubin made it impossible to ignore. She was studying the rotation of individual spiral galaxies. Logic dictates that stars at the outer edges of a galaxy should move more slowly than those closer to the bright, dense center, just as Neptune orbits the Sun more slowly than Mercury. But that is not what she found. Over and over again, in galaxy after galaxy, Rubin's meticulous observations showed that the outer stars were moving just as fast as the inner ones. It was a stunning violation of Newtonian physics. The only way this could be possible is if the galaxies were embedded in a vast, invisible halo of some mysterious substance, its mass extending far beyond the visible light of the stars. Vera Rubin had confirmed Zwicky's ghost. Today, we know that this dark matter constitutes about 27% of the total mass and energy of the universe. The ordinary matter that makes up you, me, the Earth, the Sun, and every star you can see in the night sky, all of it, amounts to a mere 5%. We are the cosmic rounding error. So what is this stuff? The honest answer is, we have no idea. We know what it is not. It is not just dim stars or cold gas. It does not interact with light or any other form of electromagnetic radiation, which is why we cannot see it. It is transparent, ethereal. It passes through us, through the Earth itself, as if we were not here, yet its gravitational influence is the architect of the universe. It is the invisible scaffolding upon which galaxies form and cluster. Without dark matter, there would be no galaxies, no stars, no planets, no us. We live and breathe because of a substance we cannot see, cannot touch, and cannot comprehend. A cosmic phantom that dictates the fate of everything. But the phantom has a partner, and it is even more perplexing. If dark matter is the universe's mysterious glue, there is another force acting as a cosmic propellant. For most of history, cosmologists debated two possible fates for the universe. Would gravity eventually halt the expansion from the Big Bang and pull everything back together in a big crunch? Or would the expansion continue forever, slowing but never quite stopping? In 1998, two separate teams of astronomers set out to settle the question. They used distant supernovae as standard candles to measure the expansion rate of the universe throughout its history. They expected to find the expansion was slowing down. Instead, they found something that turned cosmology on its head. The expansion of the universe is not slowing down, it is accelerating. Something is actively pushing space-time apart, fighting against gravity. This discovery was so shocking, so contrary to all expectation, that the scientists who found it spent months trying to prove themselves wrong. But the data was undeniable. They had discovered the effects of what we now call dark energy. This is the dominant force in the cosmos, making up an estimated 68% of everything that exists. It appears to be a property of space itself, a kind of intrinsic energy of the vacuum. As more space is created through expansion, more of this energy comes into being, which in turn pushes space to expand even faster. It is a runaway process. Imagine baking a loaf of raisin bread. The dough is space-time and the raisins are galaxies. As the dough rises, all the raisins move farther apart from each other. This is the standard model of cosmic expansion. But now, imagine that the dough itself has some magical property that causes it to expand at an ever-increasing rate. The raisins aren't just moving apart, They are accelerating away from each other. This is the universe we live in, and the implications are profound and chilling. If this acceleration continues, it points toward a lonely future. First, the distant galaxies will accelerate away so fast that their light will no longer be able to reach us. They will vanish from our sky one by one. Our cosmic horizon will shrink, leaving our own Milky Way galaxy as a solitary island in an endless, empty void. Eventually, in the most extreme scenarios, the repulsive force of dark energy could become so strong that it overcomes all other forces, tearing apart galaxies, solar systems, planets, and even atoms themselves in a final, cataclysmic Big Rip. We have discovered that the vast majority of our universe is composed of two substances that are complete mysteries, one pulling it together, the other pushing it apart in an epic, unseen cosmic battle that will determine the ultimate fate of reality itself. Beyond the grand, invisible structures of the cosmos, the strangeness also comes to us in whispers, in fleeting signals from the deep. On a summer night in 1977, at the Big Ear Radio Telescope in Ohio, astronomer Jerry Amon was reviewing printouts of data from a search for extraterrestrial intelligence. Suddenly, he saw a sequence of characters that made his heart race. It was a signal of stunning intensity and coherence, lasting for 72 seconds, broadcast on a frequency that is largely forbidden for terrestrial transmitters. It came from a narrow patch of sky in the constellation Sagittarius, and it bore all the hallmarks of a deliberate, non-natural transmission. In the margin of the printout, Amon circled the code and wrote a single word: WOW. The name stuck. For decades, the WOW signal has remained the single most compelling potential candidate for an alien message ever received. We have pointed our telescopes back to that same patch of sky countless times. We have found nothing. The signal never repeated. It was a cosmic doorbell that rang once and then fell silent forever. Was it a secret military satellite? A unique, undiscovered natural phenomenon? Or was it exactly what it appeared to be? A powerful, focused transmission from an advanced civilization which we happened to intercept for one brief, tantalizing minute. As it swept across our tiny corner of the galaxy, we may never know. It remains a singular, maddening question mark, hanging in the cosmic dark. More recently, a new auditory mystery has emerged. Since 2007, radio telescopes around the world have been detecting something known as fast radio bursts, or FRBs. These are astoundingly powerful blasts of radio waves, lasting for only a few thousandths of a second. In that tiny sliver of time, some of them release more energy than our sun does in an entire day. They are not subtle. They are the cosmic equivalent of a flashbulb going off on the other side of the universe. For years, we had no idea where they were coming from. They seemed to be random, appearing all over the sky. Then, we managed to pinpoint the origin of a repeating FRB to a tiny, unimpressive dwarf galaxy 3 billion light-years away. What could possibly generate such an immense amount of energy in a millisecond? The leading suspect is a type of neutron star called a magnetar, an object with a magnetic field so ludicrously powerful it could wipe the data from every credit card on Earth from halfway to the moon. Starquakes on the surface of these magnetars could, in theory, produce the energy we see. But other possibilities, from colliding black holes to, yes, the energy signatures of alien technology, remain on the table. The universe is shouting at us in short, brilliant bursts, and we are only just now beginning to learn the language. For most of human history, the idea of other worlds was confined to philosophy and fiction. Now, we know of thousands of them. The age of exoplanet discovery has revealed a menagerie of worlds, so bizarre they make our own solar system look tame and unimaginative. We have found planets that defy easy categorization. Take 51 Pegasi b, the first exoplanet discovered orbiting a sun-like star. It's a gas giant, a hot Jupiter, half the mass of our own Jupiter, but orbiting so perilously close to its star that its year lasts only 4 Earth days. Its surface temperature is a scorching 1,000 degrees Celsius, its atmosphere constantly being blasted away into space. This was not a world astronomers expected to find. It shattered our models of planetary formation and opened the floodgates. Since then, the discoveries have only grown more outlandish. We have found a planet named HD 189733b. From a distance, it is a beautiful, deep azure orb, much like our own Earth. But this is no welcoming water world. The brilliant blue color comes from an atmosphere laced with silicate particles. It is a world where the clouds are made of molten glass and where 7,000 km/h winds whip this glass sideways, creating a perpetual, hellish storm of flying shards. Or consider 55 Cancri E, the diamond planet. It is a super-Earth, twice our planet's size, orbiting so close to its star that its surface is likely molten. But its chemical composition is what sets it apart. It is believed to be incredibly carbon-rich. Under the immense pressures and temperatures of its interior, that carbon would be compressed into its most stable form. It is a world where a thick crust of graphite may sit atop, a mantle of pure, solid diamond, trillions upon trillions of carats. A treasure world that would incinerate any probe we sent to it. We have found planets orbiting 2 stars, like Tatooine from science fiction. We have found rogue planets, ejected from their home systems, doomed to wander the cold, dark space between stars for eternity. Each new discovery is a reminder that the universe has far more imagination than we do, and that the definition of a planet is broader and wilder than we ever conceived. The strangeness of the universe is not just in its individual objects, but in its grand architecture. When we map the positions of galaxies, on the largest scales, we expect to see a relatively uniform distribution. Instead, we find a cosmic web, a delicate filigree of galactic superclusters, and long, stringy filaments surrounding vast, empty regions of space. These are the cosmic voids, and the most terrifying of them is the Bortes void. Discovered in 1981, it is a colossal, almost spherical region of space, 330 million light-years in diameter. It is so large that if our own Milky Way galaxy were at its center, we would not have known other galaxies existed until the 1960s. It is often called the Great Nothing. This is an exaggeration. The void is not completely empty. It contains perhaps 60 galaxies, when a region of that size should contain thousands. It is a desert in the cosmos, an area of profound underdensity. How does such a gaping hole in the universe form? Our best models suggest that in the early universe, as matter began to clump together under gravity, smaller voids merged and grew, like bubbles in a rising loaf of bread. The Bortes void is simply one of the largest bubbles we have found. To stand at its edge and look in would be to witness an ocean of blackness, unimaginably vast, a silent testament to the lumpiness of creation. It is a stark reminder that emptiness is as fundamental a component of the cosmos as substance. On the other side of the scale, we have found the opposite. Immense structures, walls of galaxies bound by gravity that represent the largest known objects in the universe. The Hercules Corona Borealis Great Wall, for instance, is a galactic filament that stretches for a staggering 10 billion light-years. That is more than a tenth of the diameter of the entire observable universe. Its existence challenges our cosmological principle that the universe, on large scales, should be roughly the same everywhere. This structure is simply too big to have formed in the 13.8 billion years since the Big Bang, and yet, there it is, a cosmic continent of matter, so vast it should not be possible, a flaw in our understanding of how everything came to be. Perhaps the most unsettling discoveries are those that offer no easy answers, the ones that leave the door wide open to speculation that borders on the fantastic. Enter KIC 8462852, better known as Tabby's star. It is an otherwise unremarkable star, slightly larger than our Sun, located about 1,400 light-years away. But in 2015, citizen scientists analyzing data from the Kepler Space Telescope noticed it was behaving in a way no star should. It was dimming. Not in a regular periodic way, like a planet passing in front of it, but in strange, erratic, and massive dips. Sometimes it would dim by only a few percent. Once, its light dropped by a staggering 22%. This implies that something enormous, something 1,000 times the area of Earth, was blocking its light. Astronomers scrambled to find a natural explanation. A swarm of comets? Possible, but the sheer number of comets required to block that much light would be astronomical. An interplanetary dust cloud? Perhaps, but the dimming events are too sharp and irregular. A planetary collision? It would create a cloud of debris, but that cloud should glow with infrared heat, which we do not detect. Every conventional explanation has a problem. And so, reluctantly, some astronomers have been forced to consider the most extraordinary possibility of all. What if the object blocking the light is not natural? What if it is an artifact, a vast, artificial construction, a Dyson swarm of solar collectors, built by an incredibly advanced civilization to harness their star's energy? It is a wild, sensational idea, and it is by no means the leading theory. But the fact that it cannot be entirely dismissed, the fact that a natural phenomenon has proven so difficult to identify, is a testament to the sheer weirdness of the object. Tabby's star is a lesson. It teaches us that after centuries of observation, the universe can still present us with a mystery so profound that even the most outlandish science fiction concepts must be given a moment's consideration. From the crushing density of neutron stars to the absolute nothingness of black holes, from the invisible dominance of dark matter and dark energy to the fleeting whispers of unknown origin, from worlds of glass and diamond to voids of unimaginable emptiness, we set out to map a clockwork cosmos and found instead a carnival of wonders. Every time we build a new instrument, every time we look at the sky, in a new wavelength or with greater precision, we do not find the universe becoming simpler, more orderly. We find it becoming stranger, more complex, more surprising. Our knowledge is an expanding island in an infinite ocean of ignorance, and the larger the island becomes, the longer the coastline, where it touches the unknown. The strangest things in space are not just objects or phenomena, they are mirrors. They reflect the limits of our understanding, the fragility of our theories, and the boundless nature of what is still left to be discovered. They force us to ask the deepest questions. Are we alone? What is the ultimate nature of reality? What is our place within this vast, bewildering, and magnificent tapestry? Perhaps the single strangest thing we have ever discovered in space, amidst all the cosmic monsters and impossible physics, is a small, watery planet in the unremarkable suburbs of an average galaxy. A world that has somehow produced a species capable of looking up, of wondering, and of slowly, painstakingly beginning to understand. The greatest anomaly in the cosmos might just be consciousness itself, and our journey into the strangeness has only just begun. What if you could rewind the entire universe, not just by a few decades past the flickering images of your own memory, but further, much further? Imagine pushing the cosmic playback button, watching civilizations rise and fall, in reverse stars imploding back into brilliant clouds of dust and gas, entire galaxies reeling backward, their majestic spiral arms coiling tightly into dense incandescent cores. We would fly past the birth of the very first star's beacons of light, igniting in an otherwise perfect and silent darkness. We would witness the formation of the first atoms, a monumental event, when the universe cooled just enough for electrons to be captured by protons, calming the cosmos from a chaotic glowing fog into a transparent expanse. But we cannot stop there. To answer one of the most profound questions of our existence, we must keep rewinding. We must push past that era of first light back into the inferno, back into a time before atoms, before protons, before the very concept of a stable particle could even take hold. We are journeying to a moment so ancient, so alien it defies all our earthly intuition. We are going back to the very first millionth of a second of creation. In that fleeting, almost infinitesimal slice of time, the entire observable universe, all the galaxies, all the stars, all of us, was compressed into a space smaller than a single grain of sand. The temperature was not measured in thousands or even millions of degrees. It was a searing, unimaginable furnace of over 4 trillion degrees Celsius, a heat so extreme it makes the core of our sun seem like a distant ember. This was a universe that was not empty space dotted with things. It was a universe that was pure, unified, cataclysmic energy. Under these conditions, the laws of physics as we know them begin to fray and dissolve. The neat distinctions we make between matter and energy become meaningless. The universe was a crucible of such staggering violence and density that our everyday vocabulary fails us. Here in this primordial state lies a fundamental mystery. We are made of atoms, which are in turn made of protons, neutrons, and electrons. This is the bedrock of our physical reality. But could a proton, an entity we consider so fundamental, have possibly survived in that furnace? Could the very building blocks of our world have existed at the dawn of time? The answer physicists have come to realize is a resounding no. The universe in its first microsecond was simply too hot, too energetic, too compressed for matter as we know it to exist. So what was there, if not the familiar particles that constitute our bodies and our world? What was the universe made of? What was the original substance from which everything we see later emerged? This question drives us to the very edge of known physics, to a state of matter so exotic and so ephemeral, it has been called the secret ingredient of creation, the liquid genesis of our cosmos. To understand this primordial substance, we first need to look deeper into the heart of the matter we see today. For centuries we thought the atom was the final indivisible unit of reality. Then we discovered it could be split, revealing a nucleus surrounded by a cloud of electrons. We probed further, finding that the nucleus itself was a tight bundle of even smaller particles, the positively charged protons and the neutral neutrons. For a long time, this seemed to be the bottom floor of existence. These were the Lego bricks of the cosmos. Yet a series of astonishing experiments in the mid-20th century revealed another deeper layer to this cosmic architecture. Protons and neutrons, it turned out, were not fundamental at all. They are composite particles, tiny self-contained universes, each holding a trio of even more elementary entities. These are the quarks. They are, as far as we know, truly fundamental. They cannot be broken down or split apart. They are the final, irreducible points of reality from which all the familiar heavy matter in the universe is constructed. But these quarks are never ever seen alone. They are the ultimate prisoners of the cosmos. Within a proton or a neutron, they are locked in an inseparable embrace, bound together by a force so powerful it dwarfs every other force in the universe. This is the strong nuclear force, and it is carried by yet another fundamental particle, the gluon. The name is beautifully simple. Gluons are the cosmic glue. They are massless messengers of force, constantly flitting between quarks, weaving a web of energy so potent that it is literally impossible to pull a single quark out of its particle prison. If you were to grab hold of one quark inside a proton and try to pull it away, the energy required would be immense. The gluon field between it and its partners would stretch like an unbreakable elastic band. As you poured more and more energy into stretching that band, a bizarre and wonderful thing would happen. The energy in the gluon field would become so great that it would spontaneously transform into matter, following Einstein's famous equation E=mc2. A new quark and its antimatter counterpart would burst into existence from the field itself. The new quark would instantly bind with the ones you were trying to separate, forming a new stable particle, while the one you were pulling on would find the newly created antiquark, creating another particle. You wouldn't have isolated a quark, you would have simply created more prisoners. No matter how hard you pull, you can never liberate a single quark. This extraordinary principle is known as confinement. It is a fundamental rule of our present-day universe. Quarks are born in groups, they live in groups, and they die in groups. They are forever bound inside the larger particles. They create their individual identities subsumed within the collective. But what if there were a way to break this rule? What if you could create an environment so extreme, so cataclysmic, that the very walls of these particle prisons would simply melt away? This brings us back to the dawn of time, back to that first microsecond when the temperature was trillions of degrees. In that ultimate furnace, the energy density was so high that the clear boundaries between individual protons and neutrons could no longer be maintained. The sheer thermal violence of the environment overwhelmed even the colossal power of the strong force. The protons and neutrons jostling against each other with unimaginable force simply dissolved. They broke apart their constituent quarks, spilling out not as prisoners but as a liberated, surging, chaotic sea of fundamental particles. The gluons, no longer confined to holding just 2 or 3 quarks together, now swam freely between them, creating a frantic, seething medium. This is the state of matter we have been searching for. This is quark-gluon plasma. It is a substance unlike anything else in the universe today. It is not a gas of free particles, because the interactions between them are still incredibly strong, far too powerful for them to be considered independent. It's not a liquid in the conventional sense, though it flows with an almost perfect fluidity, with virtually zero viscosity. It's a primordial soup, a cosmic ocean of the most fundamental ingredients of reality, all mixed together in a state of beautiful and violent equilibrium. In this, plasma quarks were no longer defined by the proton they belonged to. They were simply quarks, part of a collective indistinguishable from their neighbours. The gluons formed a dynamic energetic backdrop, a fluid medium connecting everything to everything else. For a few fleeting microseconds, the universe was not a collection of things, but a single, unified, flowing substance. A perfect liquid of creation. This quark-gluon plasma was the ancestor of all the matter we see. Every single proton in the nucleus of every atom in your body, every neutron in the core of the most distant star began its existence as a set of free quarks swimming in this primordial sea. The universe we inhabit, with its intricate structures and stable matter, is essentially the cooled, crystallized remnant of that initial fiery liquid. As the universe expanded and the temperature dropped, a phase transition occurred, a moment of cosmic freezing. It was an event as dramatic and fundamental as water turning to ice. The unimaginable energy of the plasma began to dissipate. The gluons, once free, started to exert their binding power again, grabbing hold of the nearest quarks. In a maelstrom of creation, triplets of quarks were snatched from the soup and bound together, confined once more into the stable protons and neutrons that would go on to form the first atomic nuclei. The liberation was over. The age of confinement had begun, and it has defined the cosmos ever since. The primordial soup was gone, replaced by the familiar matter of our world. The entire transition from a universe of free quarks and gluons to a universe of protons and neutrons took place in a heartbeat, an ephemeral moment at the very beginning of time. Understanding this plasma is therefore not just a matter of academic curiosity. It is nothing less than cosmic archaeology. It allows us to probe the very origin of mass to understand why protons and neutrons have the properties they do. It holds the secrets to the nature of the strong nuclear force, the most powerful and least understood force in the universe. Peering into the nature of this plasma is like finding the original source code for reality. It's like an archaeologist finding not just a potsherd, but the wet clay on the potter's wheel at the moment of its shaping. It reveals the dynamic processes that set the stage for everything that followed the formation of galaxies, the birth of stars, and ultimately the chemical evolution that led to planets to life to us. We are in a very real sense the descendants of this plasma. Our existence is a direct consequence of how this primordial liquid cooled and condensed. The subtle properties of that ancient soup determine the balance of matter in the universe, a balance that allowed stars and galaxies to form at all. If that cosmic freezing had happened just slightly differently, the universe might be a cold, empty void, devoid of structure and life. The story of quark-gluon plasma is our own origin story written in the language of fundamental physics. But this presents us with a monumental challenge. This state of matter existed for only a few millionths of a second, nearly 14 billion years ago. It vanished before the universe was even old enough to be transparent to light. We cannot see it with any telescope. We cannot find a fossilized remnant of it anywhere in the cosmos. The primordial soup is gone, seemingly lost forever to the unrecoverable past. How then can we ever hope to study it? How can we test our theories and truly understand the substance that gave birth to our universe? The past is inaccessible. The direct evidence has been erased by billions of years of cosmic evolution. It would seem that the door to the first microsecond is permanently closed. And yet, what if it wasn't? What if instead of trying to look back in time, we could instead recreate it? What if we on our tiny planet in our quiet corner of the cosmos could build a machine capable of forging the very conditions of the Big Bang? A machine that could, for a fleeting infinitesimally small moment, generate temperatures of trillions of degrees, creating a brief microscopic fireball of creation. What if we could right here on Earth momentarily melt down matter into its most fundamental parts and create a droplet of that primordial perfect liquid that is the audacious goal of modern physics? To become in a way creators of microscopic universes, to build colossal engines of discovery designed not to explore the vastness of space, but the smallest, most extreme frontiers of time and energy. We are on a quest to cook up a batch of the universe's original soup to hold in our detectors for a fraction of a second, the very stuff of Genesis. The journey to understand the quark-gluon plasma is not one of passive observation, but of active, spectacular creation. And it is a journey that will take us to some of the most extraordinary machines ever built, where we collide matter at nearly the speed of a light, hoping to catch a glimpse of reality unbound. What if the most powerful force in the universe behaves like a paradox? What if it grows stronger the more you try to defeat it, yet melts away to almost nothing when you stop fighting? This isn't a riddle from ancient philosophy. It is the fundamental rule governing the heart of every atom, the law that dictates the very existence of you, me, and everything we have ever known. For centuries we sought the ultimate building block of reality, a final indivisible particle. The ancient Greeks called it atomos, the uncuttable. For 2,000 years that beautiful simple idea held. Atoms were the end of the line, the bedrock of the material world. Then, at the dawn of the 20th century, we cracked one open. Inside, we found a new cosmos, a bustling subatomic realm. We discovered a tiny, impossibly dense nucleus, orbited by a cloud of fleeting, ephemeral electrons. The dream of the uncuttable was shattered, replaced by a picture both more complex and far more elegant. Within that nucleus, we identified two residents, the proton shouldering a positive electric charge, and the neutron its neutral, slightly heavier sibling. Together they accounted for virtually all the mass of the atom. For a time this seemed to be the new foundation. Protons, neutrons, electrons. These were the Lego bricks of creation. We had finally, we thought, reached the bottom, but the universe rarely gives up its secrets so easily. The neat and tidy model of the atomic nucleus concealed a violent contradiction, a logical impossibility that threatened to unravel our entire understanding. The problem was charge. Protons are all positively charged, and as any schoolchild knows, like charges repel one another with ferocious intensity. An atomic nucleus, especially in heavy elements, is a cluster of dozens of these protons crammed into a space a quadrillion times smaller than a grain of sand. The electromagnetic force pushing them apart is stupendous, an electrostatic rage that should detonate every atom in an instant. Your own body should be exploding. The earth beneath your feet should have never formed. The stars in the sky should be impossible. And yet here we are. The universe is stable. The very existence of matter is proof that some other force, a force of unimaginable strength, must be at play inside the nucleus. It must be a cosmic superglue powerful enough to overwhelm the colossal repulsion of electromagnetism, but it must also be a ghost. Its influence had to be confined to the nucleus alone. Outside that infinitesimal domain, it vanishes completely. Gravity and electromagnetism reach across the cosmos, but this mysterious force was a phantom felt only by the particles it chained together in the heart of the atom. Physicists named it, with a certain beautiful simplicity, the strong nuclear force. It was the most powerful of the four fundamental forces of nature, over 100 times stronger than electromagnetism. The initial theories to describe it were ingenious. Scientists like Hideki Yukawa envisioned protons and neutrons playing a constant game of catch-tossing mediator particles called mesons back and forth between them. This constant exchange, this subatomic communion, was thought to be the source of the binding energy. This model worked to a degree. It explained how the nucleus held together. But as we built more powerful tools, as our vision sharpened to peer deeper into this strange new world, the picture began to fray at the edges. The proton and the neutron, once thought to be fundamental, started to reveal hints of an inner life. They weren't simple solid spheres. They had texture, they had structure. They were, it seemed, not the end of the story. They were merely the covers of a book we had not yet learned how to open. To read that book, we would need to do the unthinkable. We would need to build a machine capable of firing bullets small enough and fast enough to pierce the heart of a proton. The stage for this revelation was a 2-mile-long stretch of California soil home to the Stanford Linear Accelerator, or SLAC. Completed in the mid-1960s, it was a colossal scientific instrument, a particle cannon of unprecedented power. Its purpose was elegantly brutal: to accelerate electrons, the smallest particles we knew, to nearly the speed of a light, and then smash them into targets of liquid hydrogen, which are essentially collections of single protons. It was the ultimate act of reductionist science, a quest to understand something by hitting it very, very hard. Imagine firing a rifle at a cannonball. You would expect the bullet to ricochet off the surface cleanly, deflecting at a predictable angle from a solid uniform object. This is what physicists expected to see when their electron bullets hit the proton cannonballs. Instead, what they found in the late 1960s was astonishing. Some of the electrons passed through as if the proton wasn't there. Others were deflected slightly as expected, but a precious few, a tiny telltale fraction, bounced back at extreme angles, some almost reversing their path entirely. They had struck something small, hard, and unyielding deep inside the proton. It was the subatomic equivalent of discovering that a ball of cotton was hiding microscopic diamonds within its fluff. The proton was not fundamental. It was a composite object. It had an internal geography, a hidden population of tinier, more elementary constituents. The discovery echoed Ernest Rutherford's work half a century earlier, when he fired alpha particles at gold foil and found that the atom was mostly empty space, with its mass concentrated in a tiny nucleus. Now history was repeating itself on a far smaller scale. The proton itself was mostly empty space, with its properties originating from these point-like scattering centres. A theory to explain this had already been brewing, proposed independently by physicists Murray Gell-Mann and George Zweig. Gell-Mann, a brilliant and eccentric theorist with a love for language, had called these hypothetical particles quarks, plucking the whimsical name from a line in James Joyce's cryptic novel, Finnegan's Wake. 3 quarks for Muster Mark. The name was fitting because the model predicted that protons and neutrons were each composed of 3 of these quarks. There were different flavours of quark. Protons, it was proposed, were made of 2 up quarks and 1 down quark. Neutrons, conversely, were made of 2 down quarks and 1 up quark. It was a beautifully symmetric, almost simple arrangement, a new periodic table for the subatomic world. The results from SLAC were the smoking gun. The hardpoint-like objects the electrons were striking were the quarks themselves. We had for the first time seen evidence of the true fundamental components of nuclear matter. It was a moment of supreme triumph, a Nobel Prize-winning breakthrough that pushed the frontiers of knowledge deeper than ever before. But this triumph immediately gave birth to the most profound mystery of all. If protons are made of quarks, why couldn't we knock one out? The energies at SLAC were immense, more than enough to liberate a quark from its proton prison, if the force binding them was anything like the forces we already understood. Yet no matter how hard they smashed the protons, no matter how much energy they poured into the collisions, a free isolated quark was never seen. They saw jets of other particles streaming from the wreckage, the shrapnel of the collision, but never a single solitary quark. It was as if they were ghosts forever bound to their brethren. You could prove they were there, you could rattle them in their cage, but you could never ever set one free. This was utterly bizarre. Every other bound system in the universe could be broken apart if you supplied enough energy. An electron can be stripped from its atom. A planet can be flung from its star. A star can be ejected from its galaxy. But quarks appeared to be locked in a prison from which there was no escape. This phenomenon, which came to be known as confinement, demanded a whole new understanding of force. The theory that emerged to explain it is called quantum chromodynamics, or QCD. It is the theory of the strong nuclear force, and it is one of the most counterintuitive and spectacularly successful theories in all of science. In QCD, the force between quarks is carried by another particle, a gluon. The name is perfect gluons are the cosmic glue holding quarks together. But this is where our everyday intuition completely fails us. Unlike photons, the carriers of the electromagnetic force, which are themselves neutral gluons, carry the very charge of the force they mediate. This charge is not electrical. It's a new type of charge whimsically named color charge. Quarks come in 3 colors: red, green, and blue. These are just labels, of course. They have nothing to do with visible light. They are a way of describing how quarks feel the strong force. The rule of this world is that only colorless or white combinations can exist freely. A proton with 1 red, 1 green, and 1 blue quark is color neutral. It's a stable, observable particle, but a single red quark by itself is forbidden. The gluons that bind these quarks are themselves colored. A gluon can carry both a color and an anti-color like red and anti-blue. Because the gluons themselves are colored, they don't just travel between quarks. They interact fiercely with each other. They form a seething, roiling, self-interacting web of energy that fills the space between the quarks inside a proton. This is what makes the strong force so unique. Think of it like a rubber band made of pure energy. When 2 quarks are close together, the rubber band is slack. The force is weak. They can jiggle around inside their proton or neutron home with relative freedom, but try to pull them apart. As you stretch the distance between them, the energy in the gluon field connecting them doesn't diminish like it does with gravity or magnetism. Instead, the energy increases. The rubber band gets tighter and tighter, pulling back with ever greater force. You can pour in more and more energy, stretching the band further, but you will never break it. The field of gluons becomes a taut, powerful string of energy. Eventually you reach a breaking point. But it is not the quarks that break free. It is the gluon string itself that snaps. And when it does, the sheer energy you've poured into it following Einstein's famous ERMC2 condenses out of the vacuum and creates a brand new quark and anti-quark pair. The new quark instantly binds with the one you were trying to pull out, forming a new stable colorless particle. The new anti-quark binds with the quark that was left behind. You started with 1 proton, and in your attempt to rip a quark out, you've simply created more particles. You've made a mess, but you have not freed a quark. This is confinement. It is an absolute unyielding law of our universe. Every proton, every neutron is a tiny perfect prison. A chaotic world of quarks and gluons, forever rattling their chains, forever invisible to the outside world as individuals. For decades, this was the accepted reality. Quarks and gluons were the ultimate prisoners, and the universe we inhabit is built upon their eternal confinement. But within the mathematics of quantum chromodynamics, the very theory that explained this perfect prison lay a hint of a loophole, a clue to an escape clause. Physicists exploring the strange behavior of the strong force made a startling theoretical discovery in the early 1970s. While the force grew infinitely strong at a distance, it did the opposite at extremely close quarters. This property was named asymptotic freedom. It meant that if you could somehow squeeze quarks closer and closer together, the frantic, self-interacting web of gluons holding them would thin out. The force between them would weaken, fading into a whisper. The quarks would effectively stop noticing each other. They would become free. This was a stunning revelation. It suggested that under the right conditions, the walls of the subatomic prison could dissolve. But what conditions could possibly be extreme enough to trigger such a change? What cosmic forge could crush matter so densely that the very boundaries between protons and neutrons would cease to exist? The answer required thinking back to the most extreme environment we could possibly imagine. Not the core of a star, which is far too cold and diffuse. No, we had to rewind the clock of the cosmos itself. We had to journey back in time to the very first moments of creation, to the first millionth of a second after the Big Bang. In that primordial inferno, the universe was a maelstrom of energy and heat, at temperatures trillions of degrees hotter than the center of our sun. Matter was packed together at densities beyond all human comprehension. Under these unimaginable pressures and temperatures, The theory of asymptotic freedom predicted something extraordinary. Individual protons and neutrons could not possibly exist. They would be crushed, their internal structures obliterated, their confining walls dissolving into the searing heat. In their place, there would be something new, a new state of matter, a phase of reality we have never witnessed. It would be a seething primordial soup, a turbulent liquid-like plasma made not of atoms, not of nuclei, but of the fundamental constituents themselves. A universe filled with a free-roaming ocean of quarks and gluons, unbound, unconfined, interacting in a chaotic thermal dance. This exotic substance was given a name, the quark-gluon plasma. It was the theoretical prediction of the state of our entire universe in its very first microsecond of life. The stuff from which all protons, all neutrons, all atoms, and ultimately all of us would one day crystallize as the cosmos expanded and cooled. For years, this remarkable state of matter existed only on blackboards in the elegant equations of theoretical physicists. It was a ghost from the beginning of time, a lost state of creation. But science is not content with theory alone, and a bold, audacious question began to form in the minds of physicists around the world. What if we didn't have to look back 13.8 billion years to see this plasma? What if for just a fleeting infinitesimal moment we could recreate the conditions of the Big Bang right here on Earth? What if we could build a machine powerful enough to melt the atom to dissolve the proton, and for one brief instant liberate the prisoners locked inside? What if we could cook up a taste of the universe's primordial soup? But a fleeting glimpse into the mind of creation is not the same as a conversation. For all its predictive power, the theory of quantum chromodynamics was a map to a treasure that no one had ever seen. It was a ghost story told in the pristine language of mathematics of a universe that existed for a single incandescent breath, before disappearing for 13.8 billion years. To truly know this primordial state, to hold a piece of the first microsecond, a new kind of audacity was required. Humanity would have to build a time machine, not a machine of gears and spinning dials, but one forged from the most elemental forces we could command, electromagnetism, and the strong nuclear force. The plan was as simple in its concept as it was breathtaking in its ambition. If the early universe was a state of unimaginable heat and density, then we would have to recreate those conditions right here on Earth. We would build our own miniature Big Bangs. The idea was to take the heaviest, most stable nuclei we could find, atoms of lead, or even gold stripped bare of their orbiting electrons, and accelerate them to velocities so extreme they would warp the very fabric of time. We would hurl these atomic cannonballs at each other, unleashing a fury of concentrated energy designed to do one thing: to melt the protons and neutrons themselves, to boil the very substance of matter until it dissolved back into its constituent parts, liberating the quarks and gluons trapped inside for an impossibly short moment. The first great forge for this cosmic alchemy was built across the border of France and Switzerland, a giant buried beneath the tranquil countryside. This was CERN, the European Organisation for Nuclear Research, and its workhorse, the Super Proton Synchrotron, or SPS, was about to be repurposed for a quest of cosmic significance. Originally designed to smash single protons, the SPS was a colossal ring, a nearly 7-kilometre racetrack for subatomic particles. Now physicists and engineers face the far greater challenge of corralling and accelerating entire herds of lead ions, each nucleus containing 208 protons and neutrons. It was the difference between accelerating a single bullet and accelerating an entire freight train to the same impossible speed. The process itself is a symphony of controlled violence. It begins with a tiny piece of solid lead heated until it becomes a vapour. This lead gas is then bombarded with electrons, stripping the atoms of their own electronic shells, leaving behind the positively charged naked nuclei. These ions, now susceptible to the pull and push of magnetic fields, are injected into a series of smaller precursor accelerators. Each stage acts like another gear, another rocket booster, kicking the ions to ever higher energies, their velocity climbing in a precisely choreographed dance. Finally, they are unleashed into the main SPS ring. Here, powerful electromagnets chilled to near absolute zero steer the beam, bending its path, holding it in a perfect circle. Other devices, radio frequency cavities, deliver sharp rhythmic kicks of energy, pushing the ions faster and faster with every lap. Round and round they go thousands of times a second, accumulating energy, their mass increasing according to Einstein's famous equation until they are swollen with kinetic power travelling at 90 to 9.999% the speed of light. At this velocity, the lead nucleus, once a spherical collection of particles, is flattened by relativistic effects into a razor-thin pancake. It becomes a disk of pure energy aimed at another nucleus travelling at the same speed in the opposite direction, or at a stationary target of solid lead foil. The collision is an event of unimaginable intensity. For a fraction of a second, the energy density in a space smaller than a single atomic nucleus exceeds anything seen in the cosmos since the universe was a toddler. The temperature inside this microscopic fireball soars, reaching more than 100,000 times hotter than the core of our own sun, a temperature of several trillion degrees Celsius. At this inferno, protons and neutrons can no longer exist. Their structures fail, their bonds dissolve, the invisible glue of the strong force liquefies, and for a fleeting moment a teardrop of the early universe is born, a droplet of quark-gluon plasma. But this presented a profound, almost philosophical problem. How do you observe something that vanishes almost as soon as it appears? The lifetime of this plasma, this QGP, is measured in yoctoseconds. A yoctosecond is a septillionth of a second. It is a time scale so brief that if you were to stretch 1 yoctosecond to the length of a single second, that second by comparison would have to be stretched to a duration 5 times the current age of the universe. Light itself, the fastest thing we know, can barely cross the width of a single proton in this amount of time. The plasma doesn't just decay, it is fundamentally gone before any conventional instrument could ever hope to register its presence directly. It is a ghost in the machine, a whisper of creation. You can't take a picture of it. You can't put it in a bottle. The only way to know it was there is to study its ashes. The physicists at CERN knew they couldn't see the fire, so they resolved to build the most sophisticated smoke detectors in human history. They would have to sift through the debris of the collision, the blizzard of thousands of new particles that erupt from the fireball as the plasma cools and refreezes back into normal matter. The quark-gluon plasma itself is the crime. These particles are the forensic evidence. And so began the construction of detectors of breathtaking scale and complexity machines that were themselves triumphs of engineering and global collaboration. Experiments with names like NA49, WA97 and NA50 were not single instruments, but multi-story 1,000-ton behemoths wrapped around the point of collision. They were technological cathedrals built to witness a miracle that lasted for less than the blink of an eye. Imagine standing inside one. You're surrounded by layers upon layers of intricate technology, a 3-dimensional web designed to capture every possible clue. Closest to the collision point, the beam piper silicon trackers, pixelated sensors of extraordinary precision that can reconstruct the exact trajectory of charged particles flying out from the central fireball. These trackers act like a digital fingerprinting system, tagging thousands of pions, kaons and protons, measuring their paths as they curve in the powerful magnetic fields that permeate the entire volume of the detector. The curvature of each track tells a story revealing the particle's momentum and whether its charge is positive or negative. Further out are vast chambers filled with gas known as time projection chambers. When a particle streaks through this gas, it ionizes the atoms along its path, leaving a trail of liberated electrons like a jet leaving a contrail in the sky. An electric field draws this faint trail towards a sensor plane, and by measuring the precise arrival time and position of the electrons, a computer can reconstruct a beautiful 3-dimensional image of the particle's journey through the detector. It is a way of making the invisible visible, of painting a portrait of the collision's immediate aftermath. Beyond these tracking systems lie the calorimeters, the heavy hitters of the detector. These are dense, massive blocks of materials like lead, glass or iron, interleaved with scintillating plastics or liquid argon. When a high-energy particle slams into a calorimeter, it initiates a cascade, a shower of secondary particles, transferring all of its energy into the detector material. This energy creates tiny flashes of light, or small electrical signals which are collected and measured by thousands of photodetectors. By summing up all this light or charge, physicists can determine the total energy of the original particle with incredible accuracy. They are in essence cosmic thermometers, measuring the heat of the explosion particle by particle. And finally, at the outermost layers shielded by meters of steel and concrete, are the muon detectors. Muons are heavy cousins of the electron, and they are unique in their ability to penetrate huge amounts of matter. Almost nothing else created in the collision can make it this far, so any particle that registers a hit in these final chambers is almost certainly a muon, a particle that can carry vital information from the very densest, hottest stages of the plasma's life. All of this information, millions of data points from hundreds of thousands of channels, must be read out, digitized and recorded in a fraction of a second before the next collision unleashes another storm of particles. It is a data processing challenge on a scale that pushes the limits of computing technology, generating petabytes of information, a digital deluge that teams of scientists from around the world will spend years meticulously analyzing. They are searching for patterns, for anomalies, for the telltale signatures that could only be explained by the momentary existence of that primordial soup. While the pioneers at CERN were blazing the first trails, an even more ambitious project was taking shape across the Atlantic on Long Island, New York. At Brookhaven National Laboratory, a machine was being conceived not as a repurposed instrument, but as the world's first collider built from the ground up with one singular dedicated purpose: to create and study the quark-gluon plasma. This was the Relativistic Heavy Ion Collider, or RHIC. RHIC represented a quantum leap in the technology of creation. Instead of firing a beam at a fixed target, as was often done at the ESPSRHIC, would consist of two independent intersecting accelerator rings, each over 3 kilometers in circumference. One ring would accelerate a beam of gold ions clockwise, while the other would accelerate an identical beam counterclockwise. This design was a masterstroke of physics. By colliding the beams head-on, you effectively double the available energy for the collision. It's the difference between crashing a car into a wall and crashing two identical cars into each other at the same speed. The resulting impact is exponentially more violent. RHIC could accelerate gold nuclei even heavier than led to energies more than 10 times greater than the SPS. This wasn't just an incremental improvement, it was a new regime. It was the difference between creating a fleeting marginal state and creating a robust, definitive, and long-lived droplet of the early universe. If the QGP was a fragile flicker at CERN, RIC was designed to ignite a sustained roaring fire. Circling this colossal machine were its own cathedral-like detectors, Star and Phoenix, even larger and more sophisticated than their European predecessors. They were built by a global consortium of thousands of scientists representing the culmination of decades of research and development in particle detection. They were designed to answer the questions that the ESPS experiments had first posed to measure the properties of this new state of matter with unprecedented precision. But before the first beams were ever circulated, before the first collisions were recorded, the entire community of physicists had a very clear idea of what they expected to find. There was a target, a theoretical prediction, that served as the benchmark for discovery. The prevailing wisdom drawn from the fundamental equations of quantum chromodynamics was that the quark-gluon plasma should behave like a gas. This was the most straightforward and elegant prediction. The theory described quarks and gluons as being asymptotically free. This means that when they are packed together at incredibly high energies and temperatures, the strong force that binds them together becomes paradoxically weak. Freed from their confinement within protons and neutrons, the quarks and gluons should essentially stop noticing each other. They should fly around freely inside the fireball, interacting only weakly and occasionally, like the molecules in a hot gas or a puff of steam. This state was termed an ideal gas of quarks and gluons. This theoretical model made clear testable predictions. If the QGP was a gas, it would have very little internal cohesion. When the fireball exploded, it should expand uniformly in all directions, like a conventional explosion in empty space. The particles flying out would show a spherical distribution with no memory of the initial shape of the colliding pancake-like nuclei. Furthermore, a high-energy quark or gluon created in the initial impact, what physicists call a jet, should be able to punch through this gaseous plasma with relative ease, losing very little energy along the way. Like firing a bullet through a thin fog, the jet would emerge on the other side largely unscathed, providing a clear signal in the detectors. This was the picture a weakly interacting transparent gaseous plasma, a perfect quark-gluon gas. It was a beautiful, simple and compelling hypothesis. It gave the thousands of physicists working at CERN and Brookhaven a clear target to aim for. Their mission was to measure the pressure, the flow and the transparency of the plasma, and compare it to the predictions of this ideal gas model. The stakes were enormous. Decades of work, billions of dollars in investment, the careers of an entire generation of scientists, all funneled into these monumental experiments buried deep underground. Vast collaborations of people from dozens of countries speaking different languages united by a single burning question. They had built the most powerful microscopes in history to peer into the heart of the hottest, densest matter ever created by human hands. The rings were built. The detectors stood ready, silent and waiting. The teams of physicists gathered in their control rooms, the atmosphere thick with a tension that had been building for years. The moment of truth was approaching. The countdowns began, and with the press of a button, the first beams of gold and lead ions were sent on their collision course. Now all that was left was to see what the universe had to say. Would the ashes of their miniature Big Bangs reveal the simple, elegant, gaseous state of matter they had all been expecting, or had creation prepared a surprise for them? And so with the colossal magnets humming their song of immense power, the first golden ions, accelerated to within a whisper of light's own unreachable speed, met their moment of destiny. Deep within the heart of the star and Phoenix detectors, silent witnesses built of silicon and wire, two shimmering disks of matter, each a nucleus of nearly 200 protons and neutrons, were on a collision course with creation itself. For a fraction of a nanosecond, the beams crossed. The universe held its breath, and then a fire was lit. A conflagration hotter than 1 trillion suns, a temperature unseen since the first tick of the cosmic clock. On computer screens in the control room, a silent explosion bloomed. Thousands of newly born particles erupted from the point of impact, a firework display of raw existence, their trajectories painted in threads of digital light. This was it, the culmination of a decade of work of immense intellectual and engineering effort. The physicists had opened a window back to the dawn of time. They had for an infinitesimal moment liberated the quarks and gluons. But as they sifted through this storm of subatomic debris, an unsettling anomaly began to emerge from the data, a subtle pattern that simply should not have been there. The theories, the elegant equations of quantum chromodynamics that had so successfully described the subatomic world for decades had made a clear prediction. When the quarks and gluons were freed from their proton and neutron cages, they would behave like a gas. A chaotic, weakly interacting plasma where each particle, buzzing with incredible energy, would mostly ignore its neighbours, flying outwards from the collision point in a random disorganised spray. Think of it as a microscopic explosion of dust. The particles should have scattered in every direction with little memory of their origin. And for head-on collisions where the two gold nuclei met perfectly, this is more or less what the detectors saw, a uniform spherical bloom of new matter. But perfect dead-center collisions are extraordinarily rare. The vast majority of the time, the two pancake-shaped nuclei would clip each other, striking off-center. In these more common events, the zone of annihilation, the initial fireball, wasn't a perfect sphere. It was an elongated almond-like shape, a compressed oval of pure energy. If the resulting quark-gluon plasma were truly a gas, this initial shape wouldn't matter. The liberated particles barely interacting would still fly outwards in a mostly random spherical pattern, quickly forgetting the elliptical geometry of their birth. The data, however, told a completely different story. It whispered of a deep and powerful conspiracy among the particles. As the scientists meticulously reconstructed the flight paths of the thousands of particles emerging from these off-center collisions, they saw that the final spray was not spherical at all. It was itself an ellipse. More particles were flying out along the narrow ends of that initial almond shape than along its wider middle. This collective coordinated movement is what physicists call elliptic flow. It was as if every single quark and gluon in that fleeting instant of freedom had somehow communicated with every other particle across the entire fireball. They knew with an impossible intimacy the overall shape of the plasma they were a part of. They were not behaving like a chaotic gas of individuals. They were moving together, flowing as one. It was a stunning, confounding result, The only way to generate such a powerful collective flow is if the particles are interacting with each other with ferocious intensity, pushing and pulling on their neighbours, translating the pressure gradients of that initial almond shape into a coordinated directed momentum. The particles weren't a gas, they were behaving like a drop of liquid. Imagine throwing a handful of fine sand against a wall. The grains fly off independently, scattering in a random cloud. Now imagine throwing a water balloon. The liquid inside, upon impact, flows. It responds to the pressures and shape of the container splashing outwards in a coherent collective sheet. The particles emerging from RHIC were not the sand, they were the water. This realization sent a shockwave through the nuclear physics community. For years, the guiding principle had been a concept called asymptotic freedom, the Nobel Prize-winning idea that the strong force, the glue that binds quarks, paradoxically gets weaker as quarks get closer together. At the unimaginable energies and densities inside RHIC's fireballs, the quarks and gluons should have been so close, so energetic, that the strong force between them would have all but vanished. They should have been free. They should have formed a near-perfect gas. But the evidence of this collective flow was undeniable. The data clearly showed that instead of becoming weaker, the interactions were more powerful than anyone had ever imagined. The quarks and gluons weren't ignoring each other. They were tangled in a vibrant, intricate, and incredibly strong dance. The soup of the early universe, it turned out, was not a thin, watery broth. It was something far more substantial, something with a texture and character that defied all expectation. To quantify just how liquid-like this new state of matter was, scientists had to measure its viscosity. Viscosity is in essence a fluid's internal friction, its resistance to flow. Think of honey. It's thick and slow-moving because its molecules cling to each other, creating immense drag. It has high viscosity. Water, by contrast, flows easily. It has a low viscosity. An ideal gas has virtually no collective flow, and thus an effectively high resistance to it. The initial prediction for the quark-gluon plasma was that it would be a rather sluggish, high-viscosity substance if it behaved like a fluid at all. But the strength of the elliptic flow measured at RHIC pointed to the exact opposite. The flow was so efficient, so perfectly translated from the initial geometry to the final particle distribution, that the plasma had to have an astonishingly low viscosity. The internal friction had to be almost zero. The quarks and gluons were moving past each other with an ease that seemed to defy logic, yet they were so strongly coupled that they moved as a single unified entity. It was a baffling paradox. How could something be both intensely interactive and incredibly slippery at the same time? As the teams at RHIC refined their measurements, the numbers they calculated grew more and more extreme. The viscosity was low, then it was shockingly low. Finally, they arrived at a value so close to zero it seemed impossible. It was approaching a theoretical limit, a fundamental flaw predicted by certain branches of quantum physics and string theory. This limit, known as the Covington-Starinetz KSS bound, represents the lowest possible viscosity any fluid in the universe can have a kind of quantum mechanical speed limit for fluidity. No substance, no matter how exotic, should ever be able to cross this line. And here in the debris of shattered gold atoms was a substance that was brushing right up against that ultimate boundary. The quark-gluon plasma was not just a liquid. It was, for all intents and purposes, a perfect liquid, the most ideal frictionless fluid allowed by the laws of nature. This was the bombshell discovery. It was as if we had set out to find a puff of steam and had instead found a substance more fluid than anything ever encountered on Earth, more fluid than the super-cold helium that climbs the walls of its containers, more fluid than the core of a neutron star. It was the most perfect liquid in the universe. The announcement, first made public in 2005, was a watershed moment in physics. It fundamentally rewrote our understanding of the strong force. The simple picture of asymptotic freedom, while true at even higher energies, was clearly not the whole story. Under the conditions of the early universe, the strong force manifests not as a weakening bond, but as a perfect collective embrace. The quarks and gluons are not freed into a lonely chaos. They are liberated into a seamless quantum liquid, a state of matter where the very idea of an individual particle begins to dissolve. Each quark is so intimately connected to its neighbours through a constant furious exchange of gluons that the entire system acts as a single indivisible whole. It's a quantum entanglement on a macroscopic scale, a droplet of reality where every part knows what every other part is doing instantaneously. This discovery provided the first truly compelling smoking gun evidence that RHIC had indeed created the quark-gluon plasma. The unique paradoxical properties of this perfect liquid could not be explained by any other known physics. It was the signature of a new frontier. Forcing this radical shift in thinking wasn't easy. The community was gripped by a period of intense debate and scrutiny. Every line of code was checked, every assumption questioned, every alternative explanation rigorously pursued and ultimately discarded. The data was simply too clean, the signal too strong. The 4 major experiments at RHEC Phoenix Star, Phobos and Brahms, all working independently with different detector technologies and analysis techniques, arrived at the same inescapable conclusion. The liquid was real. The implications rippled outwards far beyond the confines of nuclear physics. String theorists working on abstract ideas connecting gravity in higher dimensions to quantum field theories were stunned to see that their esoteric equations had predicted the viscosity bound that RHIC had just measured. The quark-gluon plasma suddenly became a tangible experimental testing ground for some of the most advanced and speculative ideas about the fundamental nature of reality, a bridge between the world of particle collisions and the arcane mathematics of black hole horizons. It was a convergence of theory and experiment that happens only a few times in a century a moment, when disparate fields of inquiry suddenly lock together, revealing a deeper hidden unity in the cosmos. But the most profound consequence of this discovery was what it told us about our own cosmic origins. It gave us a new language, a new metaphor for describing the birth of our universe. In that first critical microsecond after the Big Bang, before the first protons and neutrons could ever form the cosmos, was not a frantic hot gas of disconnected particles. It was a silent, seamless, and utterly perfect liquid. Imagine that. The entire observable universe, a vast, expanding droplet of this primordial fluid, flowing without friction, without turbulence, a silent, unified quantum object. The tiny density fluctuations present in this liquid, the subtle currents and ripples in its perfect flow would later be frozen in place as the universe cooled and the plasma condensed into the familiar matter of protons and neutrons. These primordial ripples born in a perfect liquid would become the seeds of everything we see today. They were the gravitational blueprints for the first stars, the first galaxies, and the great cosmic web of clusters that stretches across the heavens. The elegant flowing nature of the universe's first moments is imprinted on the very architecture of the cosmos. When you look at the grand tapestry of galaxies, you are seeing a fossilized echo of that initial perfect fluidity. The discovery at RHIC didn't just answer a question, it unlocked a dozen new ones, each more tantalizing than the last. Why is the plasma a perfect liquid? What is it about the strong force at this specific energy scale that creates such an exquisitely coordinated yet frictionless state? Is this liquid nature a universal property of all strongly interacting quantum systems, from the cores of neutron stars to the physics near a black hole's event horizon? The perfect liquid was not an endpoint. It was a gateway. It was a clue that the strong force held deeper complexities, more emergent collective behaviours than our theories had ever led us to believe. It showed us that by smashing matter apart, we could reveal not chaos, but a profound and unexpected form of order. We had peered into the crucible of creation and found not the fiery anarchy we expected, but a silent, flowing and perfect state of being, a quantum liquid from which the solidity of our world would eventually crystallize. The challenge now was to understand the anatomy of this perfection, to probe its structure and uncover the hidden rules of its quantum choreography. The Large Hadron Collider in Europe was already preparing to enter the stage, ready to create its own droplets of this primordial fluid at even higher energies, pushing this strange new world to its absolute limits. And so, the startling revelation settled upon the world of physics not with a whisper, but with the force of a tectonic shock. The primordial state of the universe, this soup of quarks and gluons we had pursued for decades, was not the chaotic free-for-all gas we had long envisioned. It was a liquid. a perfect liquid flowing with almost zero viscosity, a substance so coordinated, so intrinsically connected it moved as one. This discovery was more than a mere detail. It was a fundamental shift in our understanding of matter at its most extreme. It meant that in the universe's first microsecond existence wasn't a frenzy of individual particles, but a collective, a unified flowing whole. But to declare it a liquid is one thing. To truly know it, to map its properties, to take the measure of a ghost that vanishes almost as soon as it appears, that is another challenge entirely. How do you chart the geography of a droplet that exists for only a few millionths of a billionth of a billionth of a second? How do you take the temperature of a fire that burned for an instant 14 billion years ago? You cannot build a barometer or a thermometer small enough or fast enough to probe this state directly. The quark gluon plasma is a phantom, and to study a phantom you cannot touch it. You must observe the way it disturbs the world around it. You must learn to read the subtle imprints it leaves behind, the echoes it casts into the future. The physicists at the relativistic Heavy Ion Collider and the Large Hadron Collider had to become cosmic detectives, sifting through the debris of their miniature Big Bangs for clues for fingerprints left on the scene of creation. They had to invent entirely new ways of seeing, turning their colossal detectors not into microscopes but into exquisitely sensitive instruments for reconstructing a memory. The first of these revolutionary techniques was born from a simple geometric insight. When two gold or lead nuclei accelerated to near the speed of light collide, they rarely meet in a perfect head-on strike. More often, they graze one another a glancing blow, where the two spherical nuclei overlap to create a brief almond-shaped interaction zone. This initial shape, this ephemeral ellipse of superheated energy, is the key. Inner gas particles would fly out from this zone, randomly expanding uniformly in all directions like a puff of smoke retaining no memory of that initial almond shape. But in a liquid, something profoundly different happens. A liquid has pressure. The compressed elliptical fireball of the quark gluon plasma experiences an immense internal force, a pressure greater than anything found in the universe since. And this pressure is not uniform. The almond shape is shorter along one axis than the other, creating a pressure gradient. The push is stronger along the shorter, more compressed axis. As a result, the particles don't fly out randomly. They are collectively propelled outwards, flowing together with more force, more momentum along that path of least resistance. They are pushed into a coordinated directed motion. This phenomenon, this collective anisotropic expansion, is what physicists call elliptic flow. It is the first unambiguous signature of a liquid. We aren't seeing the liquid itself. We see its effect. We see the final distribution of the thousands of pions, kaons, and protons that stream into our detectors, and we find that their paths are not random. They carry a collective memory of that initial shape, a shared directionality imposed upon them by the coordinated push of a fluid. To witness this is to see the ghost breath misting up a cold window. The particles streaming into the detectors are the mist, and their collective pattern is the undeniable proof of the breath that expelled them. The strength of this flow, how pronounced the effect is, tells us just how perfect the liquid is. A thick, viscous liquid like molasses would damp out this effect, the internal friction resisting the collective motion. But the quark gluon plasma showed an elliptic flow so strong, so pronounced, that it was consistent with a fluid having almost zero viscosity or internal friction. This was the origin of the term perfect liquid, a substance that flows more freely than any other known to science, even superfluid helium. We were meticulously measuring the hydrodynamic properties of a substance that lasted for 10 to the minus 23 seconds. It was an act of staggering intellectual audacity, reconstructing the fluid dynamics of the infant cosmos from the fossilized trajectories of its shrapnel. But understanding its collective behavior, its perfect fluidity, was only the first step. To truly characterize this primordial state, we needed to get inside it. We needed a probe. We needed a way to measure its density, its opacity, to understand what it was like to travel through the newborn universe. The solution was a stroke of genius, an experiment within an experiment. As the two heavy nuclei collide and dissolve into the quark gluon plasma, the immense energy of the impact occasionally triggers a much smaller, far more violent event deep inside the fireball. A single pair of quarks or gluons can collide with such ferocious energy that they recoil, flying apart in opposite directions at nearly the speed of light. In a normal vacuum, like in a simple proton-proton collision, these two recoiling particles would blaze outwards, rapidly creating a cascade of new particles around them as their energy converts into matter. These two back-to-back high-energy sprays of particles are known as jets. They are perfectly balanced, a matched pair carrying equal energy and momentum, a beautiful testament to the conservation laws that govern our universe. But inside the quark-gluon plasma, the fate of these jets is radically different. They become our messengers from the interior. One jet born near the edge of the fireball might escape relatively unharmed, streaking out into the detectors as a brilliant concentrated spear of energy. But its twin born at the same instant and with the same power is pointed in the opposite direction. It must travel through the seething, ultra-dense medium of the plasma. It is like firing two identical bullets in opposite directions. One flies through the air, the other is fired into a deep, dense ocean. The bullet in the air travels true. The bullet in the water is immediately met with immense resistance. It slows, it tumbles, its energy is rapidly absorbed by the surrounding medium. This is precisely what happens to the jet inside the quark-gluon plasma. As it plows through this perfect liquid, a substance 100,000 times hotter and orders of magnitude denser than the core of our Sun, it interacts violently with the free quarks and gluons. It loses energy at a staggering rate, its momentum bleeding away into the plasma, creating a shockwave, a sonic boom in the fabric of the early universe. This process is called jet quenching. It is the single most powerful tool we have for probing the internal properties of the plasma. And what the experiments found was breathtaking. They would detect one powerful high-energy jet bursting from the collision, but when they looked for its partner on the opposite side where an equally powerful jet should have been, they often found nothing. Or at best, a faint diffuse spray of low-energy particles, the scattered, exhausted remnants of a once mighty particle beam. The second jet was gone. It had been completely swallowed, its energy totally absorbed by the primordial fluid. This was the smoking gun. It proved beyond any doubt that the quark-gluon plasma was not just a liquid, but an incredibly dense and strongly interacting one. It was opaque. The universe in its first moment of existence was a fog so thick that not even its own fundamental particles could travel through it unimpeded. The degree of quenching, the exact amount of energy the jet loses, becomes a direct measurement of the plasma's properties. By comparing the energy of the surviving jet to the ghost of its quenched twin, we can calculate the density and the interaction strength of the medium it traversed. We are performing a kind of cosmic tomography, sending a beam through a substance to map its interior, just as a CT scan uses X-rays to map the inside of a human body. We were for the first time seeing the texture of the Big Bang. With these two powerful tools in hand, elliptic flow revealing the plasma's perfect fluidity and jet quenching revealing its staggering opacity and density, we could finally begin to assemble a complete portrait of this primordial matter. We could begin to put numbers to the unimaginable. The first target was its temperature. How hot was the universe at 1 microsecond old? There is no thermometer that can survive such conditions. Instead, physicists had to become stellar astronomers on a subatomic scale. In the heart of the plasma, the frantic dance of quarks and gluons occasionally produces particles of light photons. Most of these photons are reabsorbed, but a precious few, the so-called thermal photons, manage to escape the fireball without interacting further. Like light from a distant star, these photons carry a spectral signature of their source. Their energy distribution, their colour, is a direct function of the temperature of the medium that created them. By carefully isolating and measuring these fleeting messengers, we could read the plasma's temperature. The number they found is difficult to comprehend. It is not thousands or millions or even billions of degrees. The quark-gluon plasma reaches a temperature of over 4 trillion degrees Celsius. That is more than 250,000 times hotter than the core of the Sun. It is a temperature so extreme that it represents a phase transition of reality itself, the point where the very protons and neutrons that build our world dissolve like salt in water. At this temperature, the concept of a nucleus ceases to have meaning. There is only the flowing primordial liquid. Then came the question of density. Jet quenching had already told us it was immense, but how immense? By precisely modelling the energy loss of the quenched jets, we could calculate the density of the matter they had to push through. The results were again staggering. The quark-gluon plasma is a substance so dense that a thimbleful would weigh billions of tons. It is denser than a neutron star, the collapsed remnant of a massive supernova, which was long thought to be the densest form of matter in the modern universe. For a fleeting instant inside our particle colliders, we create a substance that rivals the gravitational singularity of a black hole in its concentration of matter and energy. We had its fluidity, its temperature, its density. But one final haunting property remained its lifespan. How long does this extraordinary state of matter actually exist before it cools, expands, and freezes out into the familiar protons and neutrons of today's universe? Measuring such an impossibly short duration seems like a task for science fiction. You cannot use a stopwatch. The entire existence of the plasma is over in the time it takes light to cross the width of a single proton. The solution came not from timing it, but from measuring the aftermath and rewinding the clock. A technique called interferometry applied to the identical particles like pions that fly out of the collision allows physicists to reconstruct the size and shape of the particle emitting source at the moment it froze. We can measure the volume of the fireball just as it died. We also know from elliptic flow and other measurements how fast it was expanding. With these two pieces of information, the final size and the speed of expansion, we can perform a simple yet profound calculation. We can run the movie backwards. We can calculate precisely how long it must have taken for the plasma to expand to that final size. The answer is consistently around 300 to 400 yoctoseconds. A yoctosecond is a septillionth of a second. It is 10 to the minus 24 seconds. It is a timescale so brief it defies all human intuition, and yet we can measure it. We can confidently say that we have created and held a drop of the early universe in our laboratories for a few hundred yoctoseconds. Think of what has been accomplished. Through this subtle art of interpreting the geometric flow of particles, through the brutal power of quenched jets, through the faint glimmer of thermal photons, and through the ghostly echo of interferometry, we have done the impossible. We have built a complete identikit of a substance that no human will ever see or touch. We know its character. It is a perfect frictionless liquid. It is trillions of degrees hot. It is the densest form of matter ever created, and its entire life plays out on a timescale that makes a nanosecond look like an eternity. We are no longer just smashing particles together to see what comes out. We are cosmic engineers precisely controlling the conditions of our miniature Big Bangs. We are cosmic archaeologists meticulously reconstructing the properties of a lost world from the faintest of traces. We have captured a droplet of time from the very beginning of the universe, and have placed it under our most powerful conceptual microscopes. We have characterized its essence, but this triumph is not an ending, it is a profound new beginning. For in learning to create and measure this primordial liquid, we have forged a key, and this key opens a door to even deeper mysteries, to questions that strike at the very heart of why our universe is the way it is. Why are we here at all? The answers, we now believe, may be found flowing within the heart of this ancient perfect liquid. And so, the portrait of Genesis sketched at Brookhaven was both revolutionary and tantalizingly incomplete. Humanity had glimpsed a new state of matter, this perfect flowing liquid of liberated quarks and gluons, a substance behaving with a collective harmony that defied all prior expectations. Yet this window into creation's dawn was streaked with dust. It raised as many questions as it answered. Was this strange frictionless fluid the only form the primordial soup could take, or was it merely one state in a more complex cosmic evolution? What secrets would be revealed if we could turn up the heat, if we could compress matter beyond the colossal pressures our IC could muster, recreating a moment even closer to the singularity itself? To find out, the human quest for origins had to move journeying from the shores of America to the heart of Europe, to a place where the very architecture of reality was about to be put to its most extreme test. Deep beneath the serene countryside straddling the border of France and Switzerland, a new cathedral to science was being consecrated. This was the Large Hadron Collider, the LHC, a machine of such breathtaking scale and ambition that it seemed to belong to a future civilization. It is not merely a particle accelerator. It is a time machine built of superconducting magnets and unfathomable vacuums, a 27-kilometer ring designed to orchestrate collisions of such titanic energy that they would tear open the fabric of space-time itself. Here, the fundamental goal was to push the frontiers of knowledge on all fronts, to hunt for the Higgs boson, to search for dark matter, to explore dimensions beyond our own. But for one community of physicists, this colossal instrument had a very specific purpose. For them, the LHC was the ultimate crucible, the one place on Earth where we could forge a piece of the early universe that was bigger, hotter, and longer lived than ever before. At one of the 4 massive interaction points along this subterranean loop, a specialized sentinel was constructed, an instrument built not for the broad search for new particles, but with a singular focused mission to study the quark-gluon plasma in unprecedented detail. It is called ALICE, a Large Ion Collider Experiment. Looking at it, you don't see a telescope pointed at the heavens. You see a monument pointed at the infinitesimal, a 10,000-ton multi-layered digital eye designed to witness the birth and death of a miniature universe. It is a technological marvel born from the collaboration of thousands of scientists across the globe, a testament to what we can achieve when we unite to answer the most profound questions. Unlike the other giant detectors at the LHC, ALICE is a dedicated heavy ion specialist. Its very design is optimized to handle the sheer chaos unleashed when 2 lead nuclei, each containing over 200 protons and neutrons, are smashed together at nearly the speed of light. Imagine the challenge. The collision itself produces a maelstrom, an outward explosion of tens of thousands of particles from a single point. Capturing this fleeting pandemonium requires a device of extraordinary precision and speed. At the heart of ALICE lies the time projection chamber, a vast gas-filled cylinder that acts as a 3-dimensional digital bubble chamber. As charged particles from the plasma's decay stream through it, they leave faint trails of ionization like invisible footprints in the air. An electric field pulls these trails towards sophisticated sensors, which then reconstruct the path of each particle with exquisite accuracy. This single component is our primary lens, allowing us to trace the debris back to its violent origin to map the flow and structure of the explosion. Surrounding this core are layers upon layers of other detectors, each with a unique role. Calorimeters measure the energy of the particles, acting like cosmic thermometers. Spectrometers embedded in a giant magnet bend the paths of particles to identify their momentum and charge. Other subsystems are designed to spot the ephemeral signatures of the heaviest quarks, the charm and bottom particles which serve as special probes, deep sea divers sent into the fiery plasma to report on its conditions. Together, these components work in a perfectly synchronized symphony, a complex nervous system designed to capture a ghost. For the quark-gluon plasma that ALICE seeks to study exists for less than a trillionth of a second. It is born and gone in a flash of pure energy before it cools and freezes back into the familiar protons and neutrons of our world. ALICE can never see the plasma directly. Instead, it must perform one of the most remarkable feats of scientific archaeology imaginable. It meticulously records the final state, the thousands of particles that fly out into its detectors, and from this intricate frozen snapshot it must reverse the flow of time. Physicists must painstakingly reconstruct the narrative of the explosion, working backward from the debris field to deduce the properties of the ephemeral substance that created it. Each collision is a self-contained experiment, a single data point in a vast cosmic library. And with the LHC capable of generating millions of these collisions every second, the library of creation was about to grow at an explosive rate. In November of 2010, the moment arrived. The LHC for the first time accelerated not protons but beams of lead ions, dense atomic nuclei stripped of their electrons. Hurtling in opposite directions around the 27-kilometer ring, these ions were accelerated to 99% of the speed of light, their mass swelling, their forms flattened by relativity into glowing pancakes of nuclear matter. Then inside the heart of the ALICE detector, these 2 beams were made to cross. The resulting cataclysm was almost beyond comprehension. The energy released in this infinitesimally small volume, a space far smaller than a single atom, was nearly 3 times greater than the highest energies achieved at RHIC. The impact instantly vaporized the structures of the protons and neutrons, liberating their constituent quarks and gluons into a state of searing incandescent plasma. For a fleeting moment, a drop of the universe as it existed in the first microsecond after the Big Bang was reborn in a laboratory in Switzerland. The first results that streamed from Alice were staggering. They were a powerful confirmation of the discoveries made at RHIC, but amplified, sharpened, and brought into stunning new focus. The quark-gluon plasma created at the LHC was not just hotter, it was a qualitatively different beast. The sheer density of energy created a larger, longer-lasting droplet of this primordial matter, giving scientists a clearer and more sustained view into its bizarre properties. The most immediate confirmation concerned its nature as a liquid. The perfect fluid discovered at Brookhaven was not an anomaly. Here, at energies far exceeding those at RHIC, the plasma continued to behave like an almost ideal, frictionless liquid. In fact, it was even more perfect. The ratio of its viscosity to its entropy density, a measure of its fluidity, was found to be even closer to the theoretical minimum allowed by the laws of quantum mechanics. This wasn't just a liquid, it was the most perfect liquid known to exist anywhere in the universe. This revelation deepened the mystery. Theorists had expected that at the much higher temperatures of the LHC, the quarks and gluons would behave more like a gas, with interactions becoming weaker. Instead, they were interacting with even greater collective strength, flowing together in a unified, coherent dance. Alice's precise measurements of the outgoing particles revealed intricate patterns of collective flow, a phenomenon known as elliptic flow, where the initial almond shape of the collision zone translates into a pressure-driven directional explosion. The plasma was expanding not like a random gas, but like a powerful hydrodynamic fluid. It was as if we had discovered that water, when heated to trillions of degrees, somehow becomes even more liquid-like, its molecules clinging together with an even greater tenacity. The strong nuclear force under these extreme conditions was operating in a regime that was still profoundly puzzling, weaving the quarks and gluons into a tightly coupled, flowing fabric. But Alice could do more than just confirm. With its superior energy and more sophisticated detectors, it could push the investigation into new territory, using more powerful probes to explore the plasma's inner workings. One of the most powerful tools in this new arsenal was the study of jet quenching, a phenomenon first observed at RHIC. In the chaos of the collision, some quarks and gluons are produced with extremely high energy, destined to fly out in back-to-back, tightly focused sprays of particles called jets. These jets act like bullets fired through the plasma. By measuring how much energy these jets lose as they traverse the medium, scientists can deduce the plasma's density and opacity. It's like determining the thickness of a wall by measuring the speed of a bullet after it has passed through it. At the LHC, the jets were far more energetic, akin to cannonballs rather than bullets, and what Alice saw was astounding. The quark-gluon plasma created in the LHC was so incredibly dense and opaque that it could stop these hyper-energetic jets in their tracks. Some jets lost so much energy that they were completely absorbed, dissolving into the fiery medium without a trace. This was direct, stunning evidence of the plasma's unimaginable stopping power. The energy density was so high that it presented an almost impenetrable wall to the fundamental constituents of matter. This provided the most precise measurements yet of the plasma's properties, painting a picture of a substance more dense than a neutron star, a roiling, seething cauldron of colour charge that aggressively interacts with anything attempting to pass through it. Furthermore, Alice observed for the first time a phenomenon that had only been theorised: the plasma could actually sweep up the heaviest quarks. Charm and bottom quarks, which are many times more massive than the up and down quarks that form ordinary matter, were thought to be too heavy to be pushed around by the flowing medium. Yet Alice saw that even these behemoths were being carried along by the collective current of the plasma, like massive boulders being swept away in a primordial flood. This discovery was a testament to the immense power of the collective forces at play within this exotic liquid, demonstrating that it behaved as a unified whole with breathtaking strength. And then there was the question of temperature. Just how hot was this microcosm of the early universe? At RHIC, scientists had measured a staggering temperature of around 4 trillion degrees Celsius, a record-breaking achievement. But the LHC was built to shatter records. By carefully analysing the spectrum of thermal photons, particles of light radiating from the plasma itself, the Alice collaboration was able to take the temperature of creation's crucible, The number they arrived at was almost beyond human intuition: 5.5 trillion degrees Celsius. It is a temperature so extreme that it has no meaningful parallel in the modern universe. It is more than 250,000 times hotter than the core of our Sun. It is a temperature that has not existed naturally in the cosmos since the very first millionth of a second of its existence. In that moment, the line between particle physics and cosmology, between the study of the infinitely small and the infinitely large, dissolved completely. The team at CERN had not just recreated a new state of matter, they had precisely dialed their time machine back to a specific identifiable epoch in the history of the universe. This is the ultimate triumph of the LHC and the Alice experiment. The connection is no longer theoretical or speculative, it is direct and empirical. The data pouring out of this detector is not just telling us about the behaviour of quarks and gluons in a laboratory, it is providing the hard experimental numbers that anchor our understanding of the Big Bang. The models that cosmologists use to describe the evolution of the universe from its first fiery moments to the formation of galaxies, stars and planets are built upon a set of initial conditions. What was the viscosity of the early universe? How did it flow? How did energy move through it? For decades, these were parameters that had to be estimated, plugged into equations as educated guesses. Now we are measuring them. Here in these controlled cataclysms deep underground, we are recreating the very substance of the infant cosmos and studying its properties firsthand. The near-perfect fluidity of the quark-gluon plasma helps explain how the initial anisotropies, the slight variations in density in the early universe, were able to propagate and eventually seed the large-scale structures we see today. The incredible stopping power of the plasma informs our models of how the universe became transparent, how the fundamental forces separated, and how the first protons and neutrons could eventually form. Each new measurement of the plasma's temperature, its density, and its flow provides another crucial calibration point, refining our grand cosmic narrative and replacing speculation with certainty. The microcosm created within Alice is a Rosetta Stone. It allows us to translate the complex language of high-energy particle interactions into the epic story of cosmic evolution. It demonstrates with a power that inspires profound awe that the same fundamental laws of physics that govern a fleeting drop of matter in a detector also govern the birth of everything we know. We are in a very real sense conducting experimental cosmology. By smashing lead ions together, we are asking direct questions of the universe at its birth. We are probing the nature of the strong force when it was the only game in town, the undisputed ruler of a reality not yet complicated by atoms or molecules. The work at CERN solidifies the foundation upon which our entire cosmological model is built. It gives us confidence that when we look back with our telescopes to the faint glow of the cosmic microwave background, our theories about what happened in the fiery moments before that light was released are grounded in experimental truth. The tiniest, hottest and briefest experiments ever conducted by human beings are providing the crucial keys to understanding the largest, oldest, and most enduring story of all the story of us. It is the story of how a universe born from a featureless, searingly hot soup of quarks and gluons could cool, coalesce, and ultimately give rise to the intricate, beautiful and life-bearing cosmos we inhabit. And so from these fleeting, intricate patterns painted inside silicon detectors, our story comes full circle. We have journeyed back to the very first microsecond of existence, not through a telescope gazing across the void, but by building a time machine of unimaginable power here on Earth. This intellectual odyssey began not with a bang, but with a whisper in an equation, with the audacious, almost sacrilegious idea that we could recreate the universe's infant state. It was a dream of forging a droplet of cosmic dawn, a spark of the primordial fire that once filled all of space. We were searching for a ghost, a state of matter predicted by theory, but unseen for over 13 billion years, a form of reality so extreme it was supposed to be forever locked away in the inaccessible history of the Big Bang. To even begin this quest required a leap of faith grounded in the hard-won language of quantum chromodynamics. It demanded the construction of machines that are themselves among the most complex objects ever assembled by human hands. Consider the sheer scale of the endeavour. We had to build subterranean racetracks stretching for miles, lined with thousands of superconducting magnets chilled to temperatures colder than deep space. Within their vacuum-sealed confines, we learned to command herds of atomic nuclei elemental titans like gold and lead, stripping them of their electrons and whipping them into a frenzy. We accelerated them closer and closer to the ultimate speed limit, pouring in the energy of a freight train into a projectile smaller than a virus. The goal was a collision of such focused, calamitous violence that it could momentarily break the strongest chains in nature. We aimed to shatter the protons and neutrons themselves to overwhelm the colour force that binds quarks together with such unbreakable tenacity. For an instant, for a time so short it makes a nanosecond seem an eternity, just a few octoseconds we hoped to melt the very substance of reality. We sought to liberate the quarks and gluons from their eternal prisons, creating a state of perfect deconfinement. We were trying to make a sun not of hydrogen and helium, but of the fundamental components of matter, a sun that would burn at 4 trillion degrees Celsius, a temperature hundreds of thousands of times hotter than the core of our own star. This was not merely an experiment, it was an act of cosmic archaeology digging down through the layers of complexity to unearth the bedrock of our physical world. And what we found in that infinitesimal moment of creation was more beautiful, more complex and more surprising than our theories had ever led us to believe. We went looking for a gas. That was the prevailing wisdom, the logical assumption. When you heat something, it eventually turns into a gas. When you unchain particles, they should fly around freely, a chaotic, disorganized swarm. The early universe, we thought, must have been a simple gaseous soup of quarks and gluons. But reality, as it so often does, presented us with a far more elegant truth. The quark-gluon plasma was not a gas at all. It was a liquid, and not just any liquid. It was a near-perfect fluid, the most ideal frictionless liquid ever observed in the universe. It flowed not with the chaotic turbulence of a gas, but with a synchronized collective grace, a quantum symphony of motion. Imagine a drop of water so pure, so internally cohesive, that it ripples and expands with almost zero internal resistance. Now imagine that drop is made of the fundamental constituents of reality, and is burning trillions of degrees hot. This singular discovery reshaped our entire understanding of emergent properties in the quantum realm. It told us that the strong force, even at these unimaginable energies, where quarks are supposedly free, still exerts a powerful collective influence, weaving the particles into a correlated flowing whole. The universe in its very first moments was not a simple chaotic vapour. It was a substance of profound and subtle order, a liquid jewel of creation. From this astonishing revelation, a cascade of insights followed. We witnessed the universe's most dramatic phase transition in reverse. As our tiny fireballs expanded and cooled with explosive speed, we watched the liquid condense back into the familiar particles of our world. We saw free quarks and gluons vanish, snatched back into the confines of protons and neutrons in a process called hadronization. In that moment of refreezing, we were directly observing the genesis of the matter that constitutes you, me, and everything we can see. We were watching the mechanism that has trapped quarks for 13 billion years spring back into place. It's one thing to read about colour confinement in a textbook, to see it as an abstract rule. It is another thing entirely to see the cage door slam shut in your own detector. We learned to use this primordial substance as a diagnostic tool. We fired high-energy quarks and gluons, the most energetic particles we could create, through the heart of the plasma. We watched them struggle to push through the incredibly dense, opaque medium. This phenomenon, known as jet quenching, was like firing a bullet into a wall of honey. By measuring how much energy these probes lost, we could for the first time calculate the properties of this exotic state. We could determine its density, its opacity, its temperature, putting concrete numbers to the physics of the Big Bang's first microsecond. We were no longer speculating, we were measuring. The dawn of time had been brought into the laboratory, placed on a cosmic scale, and subjected to the rigorous scrutiny of science. We had captured a memory of creation, and for one fleeting instant held it in our hands. This journey into the past has paradoxically illuminated our path to the future. The discovery and characterization of the quark-gluon plasma is not an endpoint. It is the beginning of a new chapter in physics, the opening of a door onto a vast unexplored landscape. We have studied one specific point on a grand cosmic map, the point of very high temperature and nearly zero density, the conditions of the Big Bang. But this is just a single location on what physicists call the QCD phase diagram. This diagram is nothing less than the ultimate map of matter, charting how the stuff of protons and neutrons behaves under every conceivable condition of temperature and pressure. And most of this map remains terra incognita. Imagine a vast unknown continent. We have landed on a single beach, the hot balmy shore of the early universe, but inland beyond our sight lie towering mountain ranges and deep mysterious valleys. These are the realms of high density, the domains of crushing pressure. What happens to nuclear matter not when it's superheated, but when it's squeezed to the breaking point? What other exotic states of quarks and gluons might exist in these unexplored territories? Does the liquid plasma give way to a crystalline solid of quarks? Does it form a colour superconductor, where gluons and quarks pair up to flow with even more exotic properties? These are the questions that now drive a new generation of experiments. The great quest for the next decade of this research is the search for something called the critical point. On this map of matter, the critical point is a landmark of profound significance. It is a unique, singular point where the very nature of the phase transition changes. Below this point, the transition from normal matter to quark-gluon plasma might be a gradual, smooth crossover, but above it we believe it becomes a violent first-order transition, like water flash boiling into steam. Finding this point would be like finding the source of the Nile for nuclear physics. It would provide a fundamental benchmark for our theories of the strong force, a fixed point on the map around which all other features can be oriented. Experiments at facilities like RHIC in the United States and the upcoming FAIR facility in Germany are meticulously dialing down the energy of their collisions, stepping away from the hot shores of the Big Bang and venturing into the cooler, denser interior of the phase diagram, hunting for the telltale signals of this elusive cosmic landmark. Each new collision, at a different energy, is like a geological survey, a core sample drilled into the unknown terrain of the quantum world, hoping to strike that critical vein of new physics. And this exploration is not merely an academic exercise confined to our terrestrial laboratories. The universe, it turns out, has been running its own high-density experiments for billions of years. It has built its own laboratories, natural crucibles of extreme matter scattered across the cosmos. We call them neutron stars. These are the collapsed cores of massive stars objects so dense that a single teaspoon of their substance would outweigh Mount Everest. They are stellar corpses crushed by their own gravity to the point where atoms have ceased to exist. Protons and electrons are squeezed together to form a sea of neutrons packed tighter than in any atomic nucleus. For decades we have wondered what lies at the very heart of these incredible objects. Does the pressure at the core of a neutron star become so immense that even the neutrons themselves are crushed? Does the matter inside dissolve into a cold, dense sea of deconfined quarks? Could there be a permanent, stable ocean of quark-gluon plasma, not hot like the early universe, but cold and incredibly dense, locked away inside these gravitational prisons? Our particle colliders provide a crucial piece of the puzzle. By exploring the high-density regions of the phase diagram, we are directly simulating the physics that governs the hearts of neutron stars. The equation of state we measure in our experiments on Earth is the very same equation that determines how large and massive a neutron star can be before it collapses into a black hole. We are now living in a golden age where these two disparate fields of science, the study of the infinitesimally small and the astronomically large, are converging. When gravitational wave observatories detect the cataclysmic merger of two neutron stars, the ripples in spacetime they send across the universe carry a signature. That signature, the specific tone and decay of the gravitational chirp, is shaped by the properties of the matter inside the colliding stars. Was the matter squishy or stiff? Did it behave like a sea of neutrons, or did it show signs of transitioning into a quark matter state just before obliteration? By combining the data from our colliders with the gravitational echoes of cosmic collisions, we are beginning to perform a kind of stellar seismology, probing the interiors of these dead stars to see if they hold a quark-gluon core. We are using the universe as our ultimate detector, connecting a yocto-second-long fireball in a lab to the fate of a star millions of light years away. Beyond these cosmic connections, the study of the quark-gluon plasma continues to push at the very boundaries of our current understanding of physics at the edges of the Standard Model itself. The perfect fluidity of the plasma, for instance, remains a profound mystery. Why is its viscosity so incredibly low, approaching a theoretical minimum value derived not from nuclear physics, but from string theory and the study of black holes in higher dimensions? This unexpected link, known as the ADS-CFT correspondence, hints at a deeper holographic principle at play in the universe, a startling connection between gravity and quantum field theory. Could it be that the behaviour of this primordial liquid on Earth is whispering to us about the quantum nature of gravity and the fundamental structure of space-time? Furthermore, within the maelstrom of these collisions, we can search for subtle imbalances and rare phenomena that could signal physics beyond what we currently know. We meticulously measure the production of different types of particles, looking for tiny deviations from our predictions. Could the extreme conditions of the plasma momentarily restore broken symmetries from the universe's earliest moments? Could they reveal the existence of exotic particles or interactions that have so far remained hidden from us? The quark-gluon plasma provides a unique furnace in which to test our most fundamental theories under conditions that can be found nowhere else. It is a proving ground, a crucible not just for matter, but for our ideas about the universe itself. Our journey to understand this primordial state of matter is in the end a reflection of our own innate curiosity. It is a story of the human desire to know where we came from, to understand the chain of events that led from a singular, hot, dense point to the vast and intricate cosmos we inhabit today. We have learned that the universe was born not in a simple gas but in a perfect flowing liquid. We have learned that the force that binds our world together can, under the right conditions, be overcome, releasing a more fundamental reality. We have built machines to shatter matter only to find a deeper, more elegant form of order hidden within. We now stand at a remarkable juncture. Behind us lies a century of theoretical speculation and experimental triumph that brought the dawn of time into the laboratory. Before us lies a vast uncharted map of existence, the full phase diagram of nuclear matter, with the promise of new states, new phenomena, and new insights into the workings of the cosmos. The quest continues, driven by the same spirit that led our ancestors to look up at the night sky and wonder. The fire that we create in our colliders for the briefest of moments is the same fire from which all things were born. And by studying its embers, we learn more not only about the universe, but about our own remarkable ability to comprehend it. The story of the quark-gluon plasma is the story of a fleeting glimpse into the absolute beginning, a glimpse that has forever changed our view of the universe and our place within it.